So today what I want to do is continue with where we started last week. So talking a bit more about LV filling and diastolic function. So what I want to do today is like go to each of the stages of diastole in a little bit more detail, and then look, for example, at which are the things that are changing, which are the parameters that are changing, and how this links to physiology. So the first thing is, so this is a slide I showed you before also. So to look at, like, in a way, the different components that you have. So we know that during the ejection, what you have is that the myocardium deforms. And we know that when you look at deformation, well, first of all, deformation determines stroke volume. So this is very important. So the more deformation you have, the more stroke volume will be ejected with every time. And deformation has different components, and you will see that this is important later on also when we talk about filling, and in general when we talk about cardiac function in disease. So we have at the one hand the longitudinal component, so where the valve plane is being dragged towards the apex. That is actually the most volume efficient component of the deformation. However, that's also the one which is most prone to, for example, pressure loading, as we've been saying at some point, and which is also related, of course, to endocardial function, which is also kind of the first affected with any disease. So the longitudinal is in some ways the most normal or the most efficient, and it's the one that you will lose early on. And we will see that there's different ways to assess this. Next, we have, of course, the circumferential shortening. And then keep in mind that we always have the radial thickening, which is, of course, a kind of a passive deformation to maintain the non-compressibility of the tissue. Similarly, when we have filling, so in the diastole, what happens is that we get the longitudinal, the lengthening in this case, so where the mitral valve or the mitral plane goes up towards the left atrium. And of course, as we said in the beginning, the whole volume of the heart is normally not changing. So that means that, of course, when the mitral valve moves, that changes, of course, also the dimensions of the atrium. And that's important for filling. And so at the one hand, we have this deformation that happens. So that kind of puts the mitral valve up. But of course, during this, and partially also because of the filling of the blood, so is happening at the same time. So when we now go in a little bit more detail, so when we have the filling, so the first phase of the filling, as we say, is the early filling. And the early filling is actually a passive filling in some ways, because what happens is we have the elastic recoil of the myocardium that has been compressed during the ejection phase. And so it's the elastic components within the myocardium which are important there. As we said before, we have spring-like materials, mainly in the form of titin, which is connecting the different cells, or at least the different sarcomeres kind of to each other. And besides that, we have, of course, also the matrix, which can partially spring back, although I guess that the matrix is relatively stiff for this. But again, there's a lot of things that we don't know yet there. And so also this kind of spring effect is, of course, partially kind of compensated or determined by the overall stiffness. So the stiffer the myocardium in itself, the less deformation or the less energy can be stored in order to be used in this early filling. And we will see later on that all kind of diseases which increase in stiffness of the myocardium, you will see that they also have some filling problems, which is related to effective stiffness. And another thing that we've been saying, and that is also quite important here, is in order to have this elastic spring back of the tissue, what you need to have is that when we look at the contractile material, so your actin, myosin, so during the ejection phase, during the contraction, during force development, the actin, myosin comes together, and we have cross bridges that are kind of binding the two together and then do the effective deformation. So what is very, very important is that these cross bridges are broken down before we start this early filling. Because you can see already immediately that these cross bridges themselves, they will increase the effective stiffness or the kind of the instantaneous stiffness of the myocardium. And so if we don't have these cross bridges, then we only have the elastic material, which is there, and that is always the most efficient. So that means that in many diseases where we have a kind of delay in this cross bridge breakdown, that will make that the muscle is still stiffer at the moment that it has to do the early filling. And of course, we will decrease the early filling. So it's this period, so this passive recoil, because of tissue properties, stored energy, and also very important is, of course, the this filling happens when, of course, the mitral valve is opened. So otherwise, we are in the isovolumic relaxation. So the isovolumic relaxation period is determined by, as we said last time, how fast the pressure will decrease. The faster the pressure decreases in the left ventricle, the shorter the isovolumic relaxation time will be. If we have a very slow decrease in this pressure, for example, because the cross bridges are still connected, or because in general the tissue is very stiff, or there's not a lot of energy kind of being stored in the kind of spring of the myocardium. So that means that we have this slow kind of decrease of the pressure, and so our isovolumic relaxation period is, of course, going to lengthen. But at the moment that the pressure in the ventricle drops underneath the pressure in the atrium, of course, the mitral valve can open, and then, of course, volume or blood can start to flow in. And deformation, so filling, can only happen, of course, when there's blood flow going on. And of course, when we look at the flow itself, so the velocity of the flow will, of course, depend on the pressure gradient, because we can only have flow if we have a pressure gradient. So the higher the pressure gradient between the atrium and the ventricle, the faster or at higher velocities the blood will come in. Of course, the opening of the mitral valve, so the area at which the blood can go through, of course, that's also something which is important. So the bigger the area, the less velocity we will need, so the less pressure gradient we will need in order to get a lot of blood coming into the ventricle. If we, for example, have a mitral stenosis, so if the opening will be smaller and smaller, then of course we need a much higher pressure gradient and likely also a much higher velocity in order to get the blood through. So, and as we said, also the spring-back effect. So what is important is the change in the geometry and the pressure gradient that does the flow, that does the filling. So that is important. And so, of course, the way that the myocardium is deforming, as I just said before, will be important there also. Because if we look at the longitudinal component, what the longitudinal component does, it, of course, increases the volume of the ventricle, so making place in some way for the blood. But what also happens is that when we look at the mitral ring, when it moves upwards, of course, what happens is that even if we don't have any acceleration of blood, the motion of the mitral ring will actually make that some volume is being displaced from the atrium to the ventricle. And so that actually this kind of longitudinal function here actually helps also in having a more efficient displacement of blood from one chamber to the other without the need of a lot of acceleration, which of course we know by Newton's law is actually needing energy. So if we go through it in detail, so what I said before, so at the one hand, you have to look at the tissue, and so the way the tissue deforms. And so we have a high velocity of blood that comes in principle, and a large amount, especially in young people, this early filling is the most important because the ventricle has contracted fiercely and is still very, very elastic. So that means that then we have a very fast pressure drop here, of course, which kind of improves the filling. And when we look at young people and children, for example, what we very often see is that this early filling is actually almost doing the whole filling of the ventricle. During this early filling, of course, because as we said before, there's no valves in the pulmonary veins. So what happens is that, first of all, we got the emptying of the atrium, and the atrium can empty in volume also because of the fact we have this ring displacement, that the ring goes up. But of course, at the same time, we have also what we will call a conduit phase of the atrium, where blood is going into the ventricle, that is then immediately coming already from the lungs. So there will be quite some important flow in the pulmonary veins in the early filling, at least in a normal kind of heart. So when we look at the different signals or the different components that we can study also, so what we said before, what is important is the time point where the pressure is starting to drop. So at the moment that the pressure is low enough, then the aortic valve closes. Keep in mind, actually, and we might come back to that later on, when you really effectively look at the pressures in the ventricle, is that, of course, the pressure within the ventricle will actually become lower than the pressure in the aorta at some point, at the moment that you start to have deceleration of the aortic flow. But it is when the pressure is low enough, then the aortic valve closes. And so that's actually where we say that the kind of diastole or whatever you call it will start, because that means that here the aortic valve closes. And what we then have is we have the onset of the isoballonic kind of relaxation period. So that is a very important period. So, and that isoballonic relaxation period is while the pressure drops. So this kind of the speed at which the pressure goes down is very, very important. As we said before, that's often, when you look in the literature, that's measured as the time constant of the exponential decay, because it is, especially initially, it's an exponential decay. So the time constant tau is determining this. And so at the moment that the pressure in the left ventricle becomes lower than the pressure in the atrium, of course, here, that's the moment that we have the mitral valve opening. So between aortic valve closure and mitral valve opening, that's what we say the IVRT, so the isoballonic relaxation time. And then here is where the early filling takes place. So where the pressure in the ventricle is as low as possible. And then, of course, the pressure in the atrium is higher and the blood flows into the ventricle. And that's what we call the E wave. So when we look at the flow, the velocity through the mitral valve, then we see here. So as soon as the mitral valve opening, we start to get an acceleration. And that acceleration takes place as long as the pressure gradient between the two becomes high. And then when the pressure gradient becomes less, what we start to see is we start to see a deceleration of this. And then we have a diastasis, so where actually all the blood that could come from the atrium went to the ventricle, and we have a pressure equalization between the atrium and the ventricle, and then of course the flow is stopping. And that is what we say the diastasis phase. So that is diastasis. When we look in the pulmonary veins, what we said before is that you have this large filling wave also in the pulmonary veins at that period. So just to summarize what I said, what determines this is the intrinsic relaxation of the tissue. So the tissue properties related to myocyte cross-bridge breakdown, which should happen very early on in systole, as we said. So by half, 2/3 of systole, a lot of the cross bridge is already starting to break down. So that at the moment that we start, it's actually here what you see is at the moment that the ventricular pressure is actually starting to decrease. This is when we have the active relaxation of the tissue. And keep in mind that that's also the process that consumes energy within the cells. It's not the contraction itself, but it's the breakdown that uses ATP. So chemically, this is where you use the energy. But what is important is that this is finished by the time that the aortic valve is closing. So where we have this kind of the recoil of the tissue. So the amount of cross bridges that are broken down, and then the elastic restoring forces, as we said before, which is related to the previous contraction. So the better contraction took place. So if we have a lot of deformation during the previous contraction, then we can have a lot of restoring forces that can do this. And then, as I said before, obviously, whenever you have tissue changes, particularly scar, but also if you have deposition like amyloid or things like that, or even kind of myocyte disarray, what happens is that both these elastic forces will not be available there, and the tissue will also not have been compressed during the contraction. So neither do we have elastic material there, nor we have the deformation that would store the energy for the elastic recoil. And that will make, of course, the more we have this type of tissue, the less ability we have for this early filling. The other thing is also the ventricular size, because you can see it's like depending on how big the ventricle is, you will see then that we know is that the bigger the ventricle, the higher the stresses are there also. So that means that also intrinsically you will have in the end less ability to have the restoring forces and then get this properly done. One of the things that actually also is important is ventricular shape, although I don't think that has been studied a lot, but you can imagine already what I said before is that it's the longitudinal component which is always the most efficient for the voluming. So the more elliptical you are, probably the better you can actually use these restoring forces in order to get proper filling. So this is the kind of driving force in brackets, or the driving principle for the decrease in pressure. So to make the myocardium or the pressure in the ventricle lower than the atrium. And the better this is, the faster the pressure will go down and the lower the pressure will become. So the bigger the gradient will become, thus the better filling we will have, of course. So as we said before, besides these intrinsic properties of the relaxation or of the tissue changes, of course, the size of the mitral valve opening is important. So the better it opens, the less pressure gradient we will need in order to get a lot of volume through. So which is then especially important for calcifications, and then especially when we look at mitral stenosis. We will at some point come back to that in a little bit more detail, but you can already imagine that this is actually quite important. And so that determines the flow that comes through the mitral valve. So that determines then actually how the filling is taking place. As we said before, the upward motion of the annulus is important. So because that determines this longitudinal function and will actually be giving some additional filling properties in some ways. In order to not use too much energy to displace the volume. And then, of course, I mean, also the amount, the more blood would come from the lungs, so through the pulmonary veins, of course, the more blood can go through the atrium. Because if you would have almost no pulmonary vein flow, what would happen is you would have a very quick equalization of atrial and ventricular pressures. And that means that you can only fill that much. So as long as you still can get and kind of pressure and flow coming from the lungs, the more efficient this will be. So you see already that it is a interplay of a lot of parameters that determine in the end how much volume, how fast will get into the ventricle in the early filling period. And you see that there's different measurements or different properties that we can try to assess, which would tell us something about. So, and here is some of the things that you could check. So, for example, as we said before, looking at when the mitral valve opens. And it's actually also interesting to look at when the mitral valve opens, for example, compared as to when the tricuspid valves opens. So because it tells you something about right-left differences. So, but again, we will show some examples at some point in the future. But so the opening of the mitral valve and then partially the IVRT is of course determined by this, is so depending on the left ventricular pressure, so how quickly it can go down, and of the atrial pressure, so depending on the level of the atrial pressure, of course the mitral valve will open also earlier or later. So you will see here that the mitral valve opens early when you have a very good ventricular pressure decrease. So that means when you have a very, very normal and very elastic tissue, the mitral valve will open early. Or at the opposite, when you have very abnormal situations, namely when the atrial pressure has increased, so that's what we call when you have increased filling pressures, And you will get that, we will come back to that later on, when if the ventricle is not properly filling in the beginning, the atrium has to do everything. And what you will see is that then, in order to get filling in, for example, a very, very stiff ventricle, you need a lot of atrial contraction, will result in the end in high atrial pressures. So we have now two conditions, namely the hypernormal and the very, very abnormal, which both will make that the mitral valve opens early. And this, we will come back to that, is called at some point pseudonormalization. So this makes it already difficult sometimes to interpret this, but the most important is that you have to keep in mind that, of course, the opening time will depend on the pressure gradient, and the pressure gradient is, of course, depending on both pressures that are included, both the negative or lower going pressure in the left ventricle and the level of the atrial pressure. So when we then look at the isovolumic relaxation time, so again, it's determined by the mitral valve opening. Well, it's actually determined by this pressure gradient between the two. So if we have increased atrial pressure, what we will see is that the IVRT will go down. If we have a slower decrease of the pressure, it will lengthen. So if the pressure is dropping slower, what will happen is, of course, that the crossing of the atrial pressure and the ventricular pressure will be later, and so our IVRT lengthens. So you will see now that, again, in the beginning is, if we have abnormal relaxation, so the more abnormal relaxation, so the slower the pressure will decrease, longer the isovolumic relaxation time will lengthen. So if we see a patient with a very long isovolumic relaxation time, we know that the pressure drops very, very slowly, and the valve opens late. So lengthening of the IVRT means abnormality. But what you also see here is that if then the relaxation is so slow, and on top of this, or if in general we have very high left atrial pressures, then of course isovolumic relaxation time will shorten. So with a lot of disease, or with important disease where the atrial pressures are starting to increase, we will see that the isovolumic relaxation time will shorten and actually become very, very short at some point also. One of the things to keep in mind, we will say that later on also, is like when we look at a right ventricle, actually in a normal right ventricle, the normal right ventricle is filling or is relaxing so fast, and also because the pressure in the right ventricle already was low, that means that the crossing of right ventricular pressure and right atrial pressure during relaxation is almost instantaneously. So that means that in a right ventricle, we have almost zero isovolumic relaxation time, and that is normal. In the left ventricle, when we have zero or almost zero isovolumic relaxation time, that is highly likely very abnormal, because you can only have that when you have very high left atrial pressure. Or if you would have like a kind of super young athlete or something like that, then it could also be that the isovolumic relaxation time is very short, because of the fact that, of course, this relaxation, as we said before, the pressure decrease is very, very fast. So the isovolumic relaxation time contains very important information for early filling, since it tells us something about how the pressure in the ventricle and the pressure in the left atrium are related. Now, if we look now at the next component, so which would be the early filling wave in the mitral valve, so that is if we measure with Doppler the flow in the mitral valve, so that's what we call the E wave, so the early wave, that's the E wave. Now, the maximum velocity of this E wave is obviously also determined by the pressure difference of the left atrium and the left ventricle. Of course, it happens a little bit later than the isovolumic relaxation time, but still the determinant is obviously, well, the determinant of any flow, as you know, is the pressure gradient between it. So again, if we would have increased left atrial pressures, so in a very sick patient that has increased left atrial pressures, not only will we have that the isovolumic relaxation time will be very short, But what also will be is that the velocity at which the blood comes in will be very high, because of course the gradient between the left atrium and the left ventricle can be very high. So in a very abnormal case, what we see is that very short isothermal relaxation time and a very fast filling. However, if on the other hand we have abnormalities, but only mild abnormalities, so if the pressure drop is only very, very slow, so what we have there is, as we said before, we have a very long isothermal relaxation time, but also at the same time, of course, this pressure gradient between the left atrium and the left ventricle will never become extremely high, and we will see that the maximum velocity will decrease. So again, what you see here is this kind of non-linear or pseudonormal effect, where we see that if we have an abnormality in the relaxation, so if the pressure drops slower than normal in the left ventricle, what we will see is that we have a lengthening of the isothermal relaxation time, and at the same time, we have a decrease of the early velocity because the pressure gradient is less. If we then become more diseased, where the left atrial pressure starts to increase, what we then see is we start to see that, of course, the early velocity goes up, and at the same time, the isothermal relaxation time will become shorter again. Now, what is also important here is that, of course, the duration of this flow depends again on, of course, the pressure gradient, but now on the kind of temporal evolution of the pressure gradient. So the longer it takes for the pressure of the left ventricle and the left atrium to equalize, the longer, of course, this E wave will be. So if we have, for example, a patient which is now has like a very stiff ventricle and a very high atrial pressure, what happens now is that, of course, isothermal relaxation time will be very short. The valve will open quickly. The blood starts to get in very, very fastly because of the fact that we have a high atrial pressure, but because of the fact that the ventricle cannot or is only very slowly becoming bigger, if we have a problem with a very stiff ventricle, what happens now is that although this early velocity was very high, it will very, very quickly decrease because of the fact that we have almost immediate equalization of left atrial and left ventricular pressure. So looking at the duration, and that is mostly measured by how fast the kind of pressure decrease will be. So it's the kind of what we call the E deceleration time. So the time that it takes for the E wave to get to zero again. So that one will be determined by how fast we have pressure equalization. So that will take longer if we have a slower relaxation of the ventricle. That will be faster if we have a very stiff ventricle, which is kind of not relaxing or not able to get any volume. So we see here again that the duration now is depending on the speed of relaxation, but is also very, very dependent on the intrinsic kind of stiffness or compliance of the ventricle, which, keep in mind, this compliance has two components. As we said before, one component can be the fact that we still have at that time point cross bridges connected. So that is what I would call like a functional stiffening. But what is mostly more important is that it really is a structural stiffening where we have scar, fibrosis, deposition disease, intrinsic fiber disarray. All of these will change the elasticity of the ventricle, and not only will make that we will have less energy to store there, but also will make that, of course, that the equalization of the pressure of the atrium and the ventricle will be faster. So when we then look at the pulmonary vein, so this kind of the wave of the pulmonary vein, so this early filling wave, so what we call the diastolic wave, of course. So that one will be determined by the pressure gradient now between the lungs and the left atrium. So this will be, of course, higher if we have lower left atrial pressure. And one of the things that we will also see that might be different also depending on the size of the atrium. So because when we have bigger atria, what happens also is that, of course, the velocity of this flow can kind of change because of the whole geometry. And of course, obviously, that's also related to the pressure in the lungs. So if we would have kind of pulmonary hypertension, then it might be that the gradient over the lungs will become different. And of course, that will determine what's going on. So we can partially look at both properties of the atrium and the atrial pressure when we look at this wave, and we partially have properties of the right side of the heart also through this gradient. If we now look at the annular motion, so how fast the tissue or the annulus would move during the early filling, that obviously is determined by all of these factors that we said. So it's determined by how fast this filling is taking place. That depends on the relaxation. That depends on the atrial pressure, but it also depends, of course, intrinsically on the longitudinal function in the beginning. If there was no longitudinal contraction during the ejection period, of course, there will be no longitudinal relaxation. So that means that when we interpret this motion of the ring and we try to get diastolic parameters out of it, we have to keep in mind that, of course, it's also determined by systole. But we know by now intrinsically, systole and diastole are very tightly coupled. So to kind of come back to it, what is important is that we have some kind of estimate, or we think about pressure differences between the left ventricle and the left atrium, that these are very much determined by relaxation and determined by increased or not filling pressures. And that some of these things we can look at timing of opening of mitral valve as compared to closure of the aortic valve. We get information from it by looking at the amplitude of the early filling velocity. The duration of it also is determined by a combination of the pressure difference, but also by how fast the volume can increase. And how fast the volume can increase, of course, depends on the tissue properties. So both the intrinsic relaxation and the intrinsic elasticity of the tissue in some ways. And then we get information from the pulmonary vein flow through this, because again, this tells us something about left atrial pressures as well as some of the right side ones. So how can you look at it then when we look in clinical pressure, in clinical practice? Well, one thing is looking, for example, at ring motion. So if you take an M mode of the ring, so this is an M mode of a normal patient, so always compare to the ECG in order to see where you are. So this was the ejection phase. So what we get is, so this is actually, well, you see the view here. So this is a apical 4-chamber view from the apical side. So what we look at is we look here at the lateral ring motion. So we look how the ring during systole moves towards the transducer. So that means the ventricle is contracting, then the ring moves towards the transducer. And then in early diastole, what happens is that the ring moves away again. So in systole, it moves towards the transducer. So this means shortening of the ventricle, so during the ejection period. And then here, what you have is at the moment of mitral valve opening. So also again, look at the ECG. So aortic valve will close somewhere, probably roughly here. Then the mitral valve opens. And what we see is we have a very fast kind of springing back of the ring. You see that actually the acceleration here, so the velocity of the ring kind of moving or during the shortening is much slower than during the relaxation. So we see here is that contraction is slow. In normal cases, early relaxation is really fast. So this is this kind of spring effect that we have. And then you see you have during the diastasis period, there's no filling taking place. And then you will have here atrial contraction. We'll come back to that later on. If you have abnormal relaxation, what now happens is that very often we have actually less systolic motion, systolic forward motion. What you now see is that actually there's a long period that nothing happens. It's like the ECG is not so great here, but here's a little bit better. So likely the aortic valve will close here, and then still nothing is happening. So we have a long flat period here. That means that we have a very long isoballonic relaxation time, because the ring is not springing back. And then the ring is springing back during filling. But what you see here is that the velocity at which it springs back is even slower than the contraction phase, which is very abnormal, because normally this one should be much faster than the contraction. Here in this patient, it's much, much, much slower. And we see actually that there's no diastasis period, because here we already have atrial contraction. So already from this M mode, what we can see is that, first of all, there's likely less systolic deformation. So there is a contraction problem. There's a very long isovolumic relaxation period where there's nothing happening. So where normally early filling should take place, we don't see anything. And then we see that there's a very slow outward motion, or kind of springing back in some ways of the ventricle. So this will show that we have very abnormal relaxation, and so a very abnormal filling. And so this patient will not fill a lot in the early period. And we can actually also look at this with tissue Doppler. Right? So it actually gives us the same information where we measure the velocity of the ring. Actually, I think M mode is mostly more robust, although Doppler has a better signal to noise ratio often. So you have to see in which patient it would be better or not. And so we see here is we have when we look at the systolic wave, so we have the early kind of, or the fast kind of contraction here. And then we have a short isovolumic period. And then we have a fast recoil. So this recoil is faster. We see that the velocity of the E wave, or the E prime, as we call it in clinical practice, is higher than the systolic velocity. So that is normal. That's what you expect. And then you have very little contribution from the atrium. When we look at this diseased patient, well, first of all, we see that the systolic is abnormal. Then we see that there's a very long isovolumic relaxation. Nothing is happening here. And what now happens is that the early wave that should be very, very fast, is very slow and is much slower than the systolic wave. And what we actually see is that there's a much faster atrial wave later on, an atrial contraction component. We'll come back to that later on. So you see that from the M mode or from the kind of tissue velocity of the ring, you can already get a huge amount of information. So that's where the shape is very important. One of the advantages of this is actually that while I said that the filling velocity, so the E wave, will increase with kind of abnormal relaxation or with a very stiff ventricle, because of the fact that you have this early, very high pressure gradient between the atrium and the ventricle, because of the fact that it's so stiff that it doesn't come back, so there is no real filling, what you will see is that this E prime is actually decreasing all the time. So there's no kind of non-linear effect of E prime. And that is actually then translated later on, we come back to that probably next week, in the use of the ratio between the blood pool E and the ring E prime. And when this ratio is changing, we can say something about this patient. It's not as robust as you can have, because sometimes this E prime can be artificially kind of high. For example, if you have some kind of rocking of the ventricle, or if you have a huge volume overload, so if you have like a lot of mitral regurgitation, then even you can have a lot of motion there, while actually the intrinsic properties of the ventricle are not that great. But we'll come back to that in another section. Okay, I think that's enough for today. So what I wanted to say is, so I tried to cover the early relaxation period. The early relaxation period is very important for a patient, and it's very important to assess it, because normally a heart wants to fill early. That's what we want to look at. So, but there's a lot of things that can change this, namely the pressure gradient between the atrium and the ventricle, which is determined by how fast the pressure in the ventricle drops, or how high the pressure in the atrium is. So, and based on these, we have a different timing of the mitral valve. So IVRT is very important to assess. And then we start to have the filling. At the same time that we have the filling, we of course have the ring that starts to move. And the filling is determined by the pressure gradient between the atrium and the ventricle. So especially when we have very high atrial pressures, this can be a very large velocity. But the problem is then, of course, even if this velocity is high in the beginning, if there's no further relaxation of the ventricle, of course, we have almost immediate pressure equalization, and this filling will be short. So it could be that we have a very high E wave, but a very short E wave, which means, of course, that the integral of this, which determines the volume, can be still very small. And so also by looking at the dynamics of the ring, we can say something about how fast this is moving, but always keep in mind that, of course, ring motion in early diastole is also determined by what happened in early systole. And so you always have to compare these two in order to get kind of the complementary information. Any questions?
Yes, just one question from my side, but very nice presentation indeed. What will happen when a normal subject is exercising? So I assume that we will get rid of the diastasis, but still the pattern itself will be kind of the same, and so we will still see differences between the abnormal relaxation.
Yes, what will happen is normally what happens with exercise is that you have to increase your cardiac output, and you can do that in two ways: by increasing your stroke volume, so the volume with every heartbeat, and increasing your heart rate. So these are the two components to increase your cardiac output. Increasing your stroke volume, a normal fit person can do this by increasing the strain. So by really contracting a little bit more. You cannot increase strain a huge amount, but you can increase strain more. So what happens is that you actually increase your longitudinal function. So that means that you have more ring motion, and you will have a faster S wave also in your tissue Doppler. And of course, if you contract more, you can also mostly faster and more have early relaxation. So what you will see with exercise, that normally your S wave will increase, your ring displacement will increase, and your E prime, so your early wave will increase, and also this kind of ring displacement, of course, comes back. So we normally have an increase in the velocity of the ring, both in systole and in early diastole during exercise. Now, looking at the mitral, as you said before, the problem is now the heart rate, because if your cycle becomes shorter and shorter, what happens actually is that diastole shortens faster than systole, because systole, you still need your amount of time to do the ejection. So although normally your systolic time will decrease with exercise, it will be less compared to the filling period. And what happens is that indeed you can get rid of your diastasis at some point, and it could be that you then start to get fusion of ENA, but we'll talk about that later on. But the most important is that normally all your velocities would increase with exercise, as long as you don't have too much fusion. And then, of course, if you start to have relaxation problems, what happens is that you definitely do not get this increase. That is the most important. And sometimes even you get a decrease, because sometimes also with exercise, some individuals, and especially if you have contraction problems, they would not be able to increase their strain during systole. And then, of course, if you decrease your strain, you would also decrease your early tissue velocities. You would decrease your ring motion. And then, of course, that will also, again, will decrease the early E wave. And some people even get increased atrial pressure with it. And so that means that you will get an increase in your E wave, while at the same time, as I said before, you might have a decrease in your E prime. So looking at this dynamics, we can probably figure something out. But normally everything should increase, especially in moderate to high, if not maybe not with the super high kind of exercise, but normally everything should increase.
Thank you, Bart.
Bart, another question regarding exercise. So in exercise, if you have like an increase of aortic pressure, that can also create relaxation problems, or since it's acute, it doesn't matter so much?
No, yes. It does matter, because what happens is that if you have an increase in aortic pressure, that means that you likely have an increase in, or you will have an increase in ventricular pressure. That means that if this during exercise, because it's relatively acute, the only way for the ventricle to deal with that is by contracting longer. So when I was talking, for example, about hypertension or aortic stenosis, what you will see is that in order to overcome acute increases in pressure, well, one thing would be shape change, of course, and in order to lower the pressures and still do the deformation, or very often increase the time of your contraction. Now, if we have a shape change, as I said before, the more elliptical with a lot of longitudinal function, that is more efficient for early filling. So if we become more spherical, our early filling will decrease because of this. Secondly, if we have to contract longer, what happens is that the cross-bridge breakdown will be later, which means that we have a functional stiffening and will then also decrease the early filling. So in all cases, with all acute kind of compensation mechanisms, what you will have is that if you have an acute increase in loading, you will have a decrease of the early filling always.